So now we will be discussing about the magnetic dipole moment of a revolving electron. Now say suppose this is your nucleus N, and surrounding this in its orbit a electron. So this is the electron, this is revolving around this nucleus. So from the concept we know if this is a charge, so if electrons are moving, so there will be a current. Now let the time period of rotation for this electron, the time period be t. We know t equals to twice pi r. This is twice pi r. This is a total circumference divided by v. That is the velocity of your electron, the velocity of the electron. So now the current I is given by the total charge, which is E, divided by the time period. Now we have already established T is equal to this. So in a way we know that the current I is equal to EV. If you put the T over here, V goes up, EV upon twice pi R, where R is the radius of the orbit. Radius of the orbit. So far that we have established. Now, because of this rotation, there will be a magnetic moment, and this magnetic moment, let me denote this particular magnetic moment as mu L. Now, if you ask me why there is a magnetic moment, like in our previous video, what we had discussed is if there is a current in a loop, then we know at a distance there will be a magnetic moment. This will behave as a dipole, and so it will have a magnetic moment. So now the magnetic moment is given by mu L. So what is mu L? Mu L is nothing but your I, that is the total current into area. And what was the area? Pi r square. This was my area. Now just denote the value of I over here. If I denote or if I put the value of I, now just observe how we are taking the concept step by step. First we know the electron was revolving. Because of the movement of electron, there is a current I. Now it has a time period t. So slowly and steadily, after if there is a current in a circular loop, we know there will be a magnetic moment. So by applying this, we know magnetic moment is nothing but the current that is flowing in the circular loop into the area of the loop. So this is actually given by mu L is given by EVR, that is electron, the charge of the electron. This is the velocity, this is the radius divided by 2. So this is what we have so far. Now, if you want to look at the direction of the magnetic moment, the direction of this magnetic moment is into the plane of the paper. See, this is where the electron is revolving. So in a way, if electron is revolving over here, so current will flow in the opposite direction. So if you look at the direction of the magnetic moment, it is inside the paper, in the z-axis, inside your screen. The video which you are looking, it is inside the screen. So this is your direction of the magnetic moment. Now this can be easily arrived from your right hand rule, and I think we had a video describing the right hand rule. That is the right hand thumb rule that you can, to be precise, you can look at the right hand thumb rule. Now, if I multiply and divide the right hand side of the above expression by the electron mass, if I take the electron mass me and divide this by the electron mass me, I have, if I look closely, mu L, let me change the color. Mu L is given by E into twice me, this is twice me, this me will come over here, into MEVR, this is MEVR. Now this is equal to E into L into twice ME. Now what is L? L is given by mass of the electron into velocity into radius, and this particular L is nothing but the magnitude of the angular momentum of the electron. We know angular momentum was in a mechanics chapter was mvr. So now the angular momentum of the electron is given by L. So if I substitute this, I have this particular expression. So now the final expression, I'll write this over here. Please have a look. Let me change the color. Mu L is equal to EL upon twice ME. Therefore, mu L upon L is equal to E upon twice mass of the electron. Therefore, in a way, what we can understand from this particular derivation, if you look over here, now this is L, and this is the electron, charge of the electron. This is minus, charge of the electron minus, just not to be confused. Now, if you look at this two particular ratio, that is magnetic moment upon the angular momentum of the revolving electron, and this two ratio is known as gyromagnetic ratio. This is known as gyromagnetic ratio. And this particular ratio, if you look, this is constant. The charge of the electron is constant, and we know 2 into ME, the mass of the electron is constant. So the gyromagnetic ratio is a constant. And if you want to look at the value of this gyromagnetic ratio, the value of this gyromagnetic ratio is given by 8.8 into 10 to the power 10 coulomb per kilo. So this is a constant, and we now come to know that the magnetic moment confirms the Ampere's hypothesis of atomic magnetic moments. From this we know that the Ampere's hypothesis for atomic magnetic moment has been confirmed. Now this, according to Ampere, it helps us to explain the magnetic properties of materials. Now this gyromagnetic ratio helps us to explain why there are magnetic properties in certain materials. And if we assign the value, now we know the momentum, angular momentum was given by NH upon twice pi. Now we know the angular momentum is it can take discrete value of H upon twice pi that we have established. So if you put the value, we have, let me clear some space. I'm writing this over here. Now we know, the things that we know is this gyromagnetic ratio, this, and we know angular momentum is given by NH upon twice pi. This was Bose postulate. That is second postulate, that is all the angular momentum will have a discrete value, that is NH upon twice pi. Now this is known as the Bose quantization condition that we know. So in a way, UL, if you look at the minimum for the first orbit where n is equal to 1, you have magnetic moment is actually equal to E upon, this is charge E upon 4 pi ME. Now we have put the value of L over here. Because we know mu L was E naught, that is charge E, L upon twice ME. Put the value of L, this value of L over here, and we have the result as into H. So this is my final result for magnetic moment for minimum, that is for the first orbit. That is electron charge E divided by 4 pi mass of the electron into Planck's constant h. So this is our derivation, or you can say the understanding about magnetic dipole moment of a revolving electron. And both of this, now one confirms the other hypothesis of Bose model, and the other one confirms this particular hypothesis, that is of magnetic moment. And we also come to know from this particular derivation the magnetic properties of some of the materials.